In this video, we're going to do a problem that involves a storage element, namely a capacitor, where we find the voltage and current curves for that capacitor. And this approach we're going to use is a circuits approach that's 3 steps. One step is to find where these curves start, where the voltage and current start at t equals 0. A second step is to find where these curves end up at steady state, and then a third step is to find how long in between, how much time it takes to go from the initial condition at t equals 0 to our steady state value, okay, namely 5 time constants. So it's finding what that time constant is and then getting the total amount of time from the time constant. So when you're doing problems like this, the first thing that you need to determine is whether your storage element is gaining stored energy over time or is it losing stored energy over time. Now with capacitors, when they gain stored energy, we say that they're charging. When they're losing stored energy over time, we say that they're discharging. So to determine, which set of curves we have here, we look at the circuit and see what the situation is. And in this particular circuit, you can see that we're told the capacitor at t equals 0 has 0 volts. Well, remember that equation that we saw in an earlier lecture, that the amount of charge on the plates of a capacitor is equal to C times V. So if V is 0, that means there's no charge that's collected on the plates of that capacitor. And if there's no charge on the plates and 0 volts across the plates, that means there's no electric field and that initially there's 0 stored energy. So this switch in this circuit closes at t equals 0, and when it closes at t equals 0, it's going to connect this 10 volt source to the part of the circuit where the capacitor is. So naturally the capacitor will start to gain stored energy from that point on. So just from looking at this circuit, we can determine that in this particular case we have a charging case. So we can ignore this charging. Okay, so we're not going to have 2 decaying exponentials. What we're going to have is the voltage building up over time like this, going, a constant times 1 minus a decaying exponential, and the capacitor current's going to be decaying exponentially. So we need to find the voltage and current start points here, the voltage and current end points, and then also how long in between. So let's now find where those 2 curves start. And the way we're going to do this is we're going to draw what's called the t equals 0 plus circuit, where you put in the initial conditions of your elements and then solve your circuit for, in this case, the initial voltage and initial current for the capacitor. So this circuit here is exactly what we had previously, except we put in the initial condition of an initially uncharged capacitor. Remember our handout that shows the various initial conditions and steady state conditions. Here's when you have an initially uncharged capacitor that at t equals 0 plus it acts like a short circuit. So I've redrawn the previous circuit, the original circuit, everything the same except there's a short where the capacitor symbol was. So now if we find the voltage for that short, well, that is the voltage across the capacitor at t equals 0 plus, because that short represents the capacitor. Likewise, if I find the current for the short, that's the current for the capacitor at t equals 0 plus. Okay, so this just becomes a circuit problem just like we did earlier in the quarter, that just involves a source and a couple of resistors. So the easy one, or what should be the easy one, is that a voltage across a short by definition is just 0 volts. So you see that's the answer for the voltage across the capacitor at t equals 0 plus, it's just 0. Now to get the current, well, again, we just use knowledge that we've learned earlier in the class, where we've seen this before. where you have a resistor in parallel with the short, well, all the current, ideally all the current flows through the short once it gets to this junction point. None of it flows through this 1K. So the amount of current is just going to be the source voltage divided by the 2K resistor that's in the path of the current. Right? So you just have 10 volts divided by 2K. So 5 milliamps. Okay, so if we go back here, we now know that this voltage curve here starts at 0, and we also know that this current for the capacitor, well, this is 5 milliamps. Okay? Alright, so you see that's one analysis that we have to do to get the start points of these curves. To get where the curves end up, we do a steady state analysis. So for the steady state analysis, again, we draw the circuit as we had in the original case, but now we replace the capacitor with its steady state condition. So if we go back to our handout, an initially uncharged capacitor at steady state acts like an open circuit. So we just need to solve here the current for the open. Okay, because the current for the open, that's the same as the current for the capacitor at steady state. And I'll put in t equal to infinity here. That's the theoretical value, but as we talked about, in practice, the steady state is 5 time constants. So you could also put 5 taus here if you wanted to. And then the voltage across the open, that's the voltage across the capacitor at steady state. Alright, so again, it just becomes an analysis like we've done earlier in the quarter. The easy one, by definition, the current for an open is 0, right? Because it's not a path, so current's not going to flow through an open. And now to get V open, we could just do voltage divider, where the voltage across that open is the same as the voltage across that 1K resistor. So we would just have 10, using voltage divider, we would just have 10 volts times 1K over 3K. Alright, so that's going to come out to 3 1/3 volts. Okay, so now if we go back to our curves, the voltage that this capacitor will charge up to, this final voltage here is the 3 1/3 volts. And once it becomes fully charged to 3 1/3 volts, well, its current at steady state is going to be 0. Okay? Alright, so what's left is, well, how much time in between does it take between t equals 0 and steady state? So to find that time, we need to get the time constant. So that's our last analysis. And when you're doing a time constant for a circuit that has more than one resistor, well, now instead of this just being R, like it was in the case of the example that just had a single resistor, well, now this R is Req. And it's Req from the perspective of the capacitor. And when you find this Req, you want to eliminate sources. So you see, we eliminated this voltage source just like we do in superposition method. Okay, we replaced it with its ideal internal resistance of 0 ohms, which is a short. So now we want to get the Req from the perspective of the capacitor. Okay, and from the perspective of the capacitor, these two resistors are in parallel. Okay, if you were just to imagine a current flowing from the capacitor into this combination of these two resistors, well, once that current got inside this circle where the resistors are, it would have 2 paths to flow. Okay, and anytime you got more than one path for current to flow through elements, that's a parallel combination. So you see the Req here would just be 2k in parallel with 1k. Oops, there's a 1 here. Okay, so the 2k is in parallel with the 1k. Okay, so product over sum, we'd get 2/3 k ohms. Alright, so now the time constant, tau, would be that 2/3 k times the capacitor, which was a microfarad, if I remember correctly. Yeah, I didn't write it here, but if you look back at the original problem, the capacitor had value of 1 microfarad. Okay, this is k ohms. So k is +3, 10 to the +3. Micro is 10 to the -6. So this is going to give us milliseconds. So it's going to be 2/3 milliseconds. Alright, but then don't forget, it takes 5 taus to reach steady state from t equal to 0, right? Again, this is our practical amount of time here. So in practice, it would take, in this case, 10/3 milliseconds to reach steady state. So if we go back to our curves here, see the amount of time, this amount of time from t equal to 0 out to steady state, that's the 10/3 milliseconds. Okay, 3 1/3 milliseconds. Okay, for both curves. Okay? So you see this approach where we're using circuit analysis to solve for these curves, it's all based on your knowledge of first order differential equations, that when you have a first order differential equation, your responses, okay, in this case the responses being voltage and current, well, they're going to be exponential. Okay, now if it's charging, it's going to be this set of exponentials like we talked about. If it's discharging, it's going to be these set of exponentials. But no matter what kind of first order differential circuit I have, the various components, the way they're connected in that circuit, they're not going to alter the form of the waveforms. And we're always going to get exponentials. We're not going to get some other signal that's different than an exponential. But what the circuitry will determine, the different circuitry in that first order circuit, is where these exponentials begin, where they end, and how long it takes in between. And that's why there's the 3 steps of this method, because each step is a circuit where you're solving for one of those items that could be possibly different based on what kind of circuit you have. So we're going to do at least a couple more examples of these types coming up in the future videos that we have coming up.